So today, guys, we're going to talk about 8a, and this is just a little quick intro section into linear versus exponential. I've decided I'm not going to do a lot from chapter 8, just because there'd be so many strange formulas we'd have to use that you would almost need a graphing calculator, and the workaround and not needing a graphing calculator would force you to memorize a whole bunch of formulas or learn a bunch of formulas. And then I'd have to teach you logarithms. So we're going to kind of go easy on chapter 8, and then we'll just do 8a, and then we'll move on to the following chapter 9 section. So unit AA is growth of linear versus exponential. So basically, this is just a background section on how to kind of identify linear versus exponential growth. Almost everything that we know about population growth, whenever they're talking population growth, for example, is almost always exponential. I guess it could grow linearly, but most of the stuff we talk about grows in some kind of exponential form for populations. But anyway, so linear growth occurs when a quantity grows by the same absolute amount each unit of time. So for example, every year or every minute or every hour, or whatever they're calculating, doesn't always have to be exactly time. That's just kind of our staple. But when it grows the same amount each time, that's linear. Okay. Exponential growth occurs when a quantity grows by the same relative amount, that is, by the same percentage in each unit of time. Okay, so that one is basically working on percentage. So they grow, each of them grow in the same way, but one of them is percentage wise and one of them is actual value. Okay, so absolute amount versus same percentage. Okay. And here's just a little graph of Straight town grows by the same absolute amount each year, and power town grows by the same relative amount each year. So this is actually one where they're showing that a town could grow linearly, and another town could grow in exponential. And as you can see, the exponential graph is very, this exponential graph right here is very obvious. That's kind of in your mind. Whenever you hear the idea exponential, you should always be thinking something that grows and grows very rapidly. So it starts off, if you notice in this location right here, they're both kind of similar, right? And then all of a sudden it starts getting out of hand as we go up here. So that's the big difference between linear growth or linear decay versus exponential growth or exponential decay, is kind of not the beginning, but the ending. With decay, I think it kind of levels out at the end, and decays rapidly at first, but that's something we'll talk about as we get to it. So linear or exponential. So here's just a few examples. And again, this is just kind of an intro section. We're not going to go crazy in depth. In each of the following situations, state whether the growth or decay is linear or exponential and answer the associated questions. So part A says the number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population was 750 4 years ago, what is it today? So what I'm going to do for part A, you know what? I'll write it off to the side here. I think this will be best. What I really like to do is I like to draw a table. And this just helps me determine if it's linear or if not. So they're saying if the student population was 754 years ago, what is it today? So what we're going to do is we're going to call this time 0 and this 750. Okay. So the reason we're doing that is they said 4 years ago. So that's kind of the start of when we're going to do the calculation. So we're going to call that time 0. Okay. So what will it be next year? So in 1 year after that start, it says it's grown by 50 each year. So I already know this is going to be linear because they're saying it's growing by the same amount, not the same percentage each year. And then so this will be 850. This will be 900. And this will be 4 years from now. So this will be 950. Okay. So it grew. So it grew from 750 to 950 in 4 years. Okay. So this graph shows me, look how much it's growing by. It grew by 50, it grew by 50, it grew by 50, it grew by 50. So this table tells me right away that this is definitely something that is linear growth. So this is linear. Oops, you know what? Linear. What am I doing? I can't write linear growth. Sorry about that. Okay. The price of milk, part B, the price of milk has been rising 3% per year. If the price of a gallon of milk was $4 a year ago, what is it now? So I'm going to do it again. I'm going to do my little table. Okay, so they said the price of milk has been rising 3% each year. Okay, so if the price of gallon of milk was 4% $4 a year ago, so we're going to do year zero. That would be when it was $4, okay? And it has been rising by 3% each year. So in the next year, we're going to multiply. So what I'm going to do is I'm going to multiply 4 times 1.03. So I'm going to do 4 times 1.03, and I get $4.12, okay? Now, the reason I did 1.03 is because if I multiply 4 by 1, I get 4, right? But they said it's 3% bigger. So I did it times 103%. So this is 103%. Okay, so that means that year it was $4.12. Now, if we did it again, they didn't ask for this, right? This is the answer, right? They said 1 year from now, but I'm just going to let you guys know, what if they asked for the following year as well? Well, we would do $4.12. 4.12 times 1.03 again. And I would get $4.24 this time, okay? So obviously, okay, well, it's not quite. So let me do one more year, okay? So let me do 4.24 times 1.03. So the problem is, you guys, is that it's looking linear. It looks like it's raising 12 cents each year, but that's because of rounding. Let me show you, actually. Let me show you what I mean. So because the percentage is so small, it's hard to notice. So if I did the first year, it would be $4.12. But then if I did the next year, it would be $4.24, 0.3, or with 36 extra, okay? And then if I did the next year, it would be 4.3672. Okay, so this is showing right here. And then if I did the next year, I would get, oops, the fourth year, I'd get 4.498216. Okay, so let me do something real quick. So if you notice, from this year to this year, it grew by 12.12. But from this year to this, or from this, how do I say this? From $4.12 to $4.2436, it grew by 12 cents, but then it also had that extra 0.36. Okay, so then it grew by 24. So from here to here, it grew by 0.1224. And then from here to here, it grew by 0.12. Let's see here, what is that, 36? And then from here to here, it grew by 0.13, and then, more. So it's not growing by the same amount each year. Now, if I rounded off, it actually would have looked like it was growing almost the same. So this would have been a very deceptive one. You would have had, the reason I wrote out so many is because I wasn't noticing the change very well. So I just wanted to write out a bunch more. Now, the problem only asked us for this, but I'm just doing this in case the homework asks you to go further. Okay. The main thing is you guys notice right when you see it that it says rising percentage per year. That literally goes right back to this same percentage per year. So it's exponential growth. Okay, so this is exponential growth, and we will have $4.12. Okay. The next one says tax law allows you to depreciate the value of your equipment by $200 per year. If you purchased equipment 3 years ago for $1,000, what is the depreciated value today? So once again, so we're going to start at year zero, being 3 years ago. And they said, if you purchased the equipment 3 years ago for 1,000, so 3 years ago, that would be the initial time we're talking about. What is appreciated value today? So we have to do 1 year, 2 years, 3 years, right? And it says the equipment depreciates by $200. So this tells me that it's getting smaller. So this would be 800, this would be 600, and this would be 400, okay? So we know that it's going to be worth $400 today. And this is linear decay. Decay or decrease. Okay, so pretty straightforward. It says the memory capacity of state-of-the-art computer storage devices is doubling approximately every 2 years. If a company's top-of-the-line drive holds 16 terabytes today, what will it hold in 6 years? Okay, so I'm going to write out my little table once again. They want 6 years now. So 0, 1, 2, 3, 4, 5, 6. And again, I do the table just to help me keep track of everything. So it's very obvious, like I can just look at it and I can tell. So for this one, they said 16 terabytes today. How much will it hold in 6 years? And they said the memory capacity of state-of-the-art computer storage devices is doubling approximately every 2 years. Okay, so actually, we're only going to do, I didn't read that correctly. Sorry about that. I forgot that this was the one that I have to write. So it's doubling every 2 years. Okay, so that's kind of sneaky on their part, but what it really means is it's, so we're going to go every 2 years. But if it's doubling every 2 years, doesn't that mean it's, anyway, this is 32, this is 64, and this is 128. Okay, so did it grow by the same amount every 2 years, right? So this grew from 0 to 16. So it grew from 16 to this would be, this would be 16. This would be 32. And this would be 64. Okay, so is it doing it the same amount each time? Okay. So what would you guys say this growth would be? I would say this would be exponential growth, because it's not the same amount. So this is a way without using percentages. Now, technically doubling is, 200%, but they could try to sneak this past you because they didn't use the word percentage. But if you write out the table, you can see that it's not the same amount each year, right? It's changing by a different amount for each time frame that we're worried about. We're worried about every 2 years. So I did 0 years, 2 years, 4 years, and 6 years. That's exponential growth. And we would expect it to be 128. So it's going to start off with 128, or we'll end up with 128 terabytes after 6 years. Okay, so let's look at this last one. It says the price of a high definition TV set has been falling by about 25% per year. So right here, I'm pretty sure this is already exponential decay, but I'm going to do my little table just to be sure. So if the price is 1,000 today, that's 0 as our starting point. What can you expect it to be in 2 years? So we'll do 1 year and 2 years, okay? So it says it's falling by about 25% per year. So I'm gonna say then that means that I'm gonna take 1,000. You know what, let me go over here. I'm gonna take 1,000. I'm going to multiply that by 0.75, because if it's losing 25% of its value, that means that it's only worth 75% of what it usually is. So when you do that, you get 750. Okay. Now I'm going to do 750 times 0.75. And I get $562.50. Okay. Now here's the thing. Once again, we look, how much is it changing by? Well, it changed by 250 here, but from here to here, if we do 750 minus, we get 187. So it's not changing by the same amount each year. Now it's changing by the same percentage, but not the same value amount. So this is definitely exponential decay, and we would expect it to be worth $562.50. Okay. So hopefully that gives you guys I think there's a few homework problems that are like that. Hopefully it gives you guys a little bit to work on that. Okay, so I left space for it here, but I just liked writing it next to it a little better. Okay, so I'm not sure if I wanted to do this problem. Yeah, let's skip this one for now. Okay, so some key facts that I want you to know about exponential growth. Exponential growth leads to repeated doubling. So that's like in that previous problem, we talked about doubling. With each doubling, the amount of increase is approximately equal to the sum of all preceding doublings. Okay, and exponential growth cannot continue indefinitely. After only relative small number of doubling, exponential growth quantities reach impossible proportions. So, in another class, we might talk more about the logistic model. And in the logistic model, they basically take into account carrying capacity of populations. So like the example, I'm not going to go through all of this, but maybe I'll just talk about it. So it says, suppose you place a single bacterium in a bottle at 11 a.m. It grows and at 11:01 divides into 2 bacteria. These 2 bacteria each grow and at 11:02 divide into 4 bacteria, which grow, and at 11:03 divide into 8 bacteria, and so on and so on. Now suppose the bacteria continue to double every minute and the bottle is full at 12. The number of bacteria at this point must be 2 to the 60th power because they're doubled every minute for 60 minutes. But the important fact is that we have bacterial disaster on our hands. Because the bacteria have filled the bottle, the entire bacterial colony is doomed. I think they actually use this kind of concept. I think they use it in compost. I could be wrong, but I thought I remember it's kind of weird watching on Discovery Channel. So when they're trying to not just compost, but like other things like manure and stuff, the reason that it sterilizes itself is because the bacteria get so hot that they end up killing themselves off from the chemical reactions that's going on and everything like that. Now, this isn't exactly the same, but what they're saying is, okay, now think there's a limited amount of space inside this bottle. So if bacteria are growing at such a rapid rate, and then at this point from 11 a.m. to 2 to 12, they're saying just in an hour, it's already growing at a rate of 2 to the 60th power. Okay, so 2 to the 60th power, it might even be 2 to the 59th power, but 2 to the 60th power is a massive number. Like, I don't even know if my calculator can do that. Okay, let me do 2 to the 60th. Well, that's not right. So it did do it, and it told me that it's 1.15 times 10 to the 18th power. Okay, so now just to put that in perspective, that's 1.15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You get the idea, right? These are all zeros right here. That's how big the number is. That's how many bacteria there are at this point. Okay, so the problem is they're going to run out of I guess oxygen. They're going to run out of space. I'm not exactly sure the reasoning, but they run out of room to keep growing at this rate. Eventually, there has to become an end. So what the logistic model does is it takes into account carrying capacity of the population. Just like if you had fish that grew in a pond, at an exponential rate, eventually that pond would be filled with fish. There'd be no food left and they'd kill themselves off and they'd all die. That's what they mean by a disaster. I would have rather seen like fish in a pond or something like that, population growth, because the bacterial one, it just gets to be such a massive number. It's hard to even visualize. Okay. because the bacteria have filled the bottle, the entire bacterial colony is doomed. So that's what this is talking about right here, is exponential growth cannot continue indefinitely. Eventually, something has to slow down. So that's like populations and everything grow exponentially, but that's because we're not we're not to the point where it is indefinite, right? We're keeping track. It just can't continue forever though. With this bacterial one, it's a much easier, I guess, little vacuum where we can talk about, well, it's in this little sealed jar that eventually will run out of the ability to support the bacteria. So just keep that in mind, that the exponential growth cannot go on without bound. So that's something else you'll learn later if you take another math class regarding the logistic model. But I think I'm going to do that. I'm going to call it a day on this video. It's just a little quick video, a lot of information really, and just definitions, and then kind of ways to recognize linear versus exponential. But again, that's all I think I'm going to do from chapter 8. We'll move on to chapter 9 in the next video.